Where are we at? We're going to actually have a summary in a little bit about where we're at, but our goal for right now is to say we'd like to come up with yet another way that we can solve an ordinary differential equation, a first order ordinary differential equation. We'd like just one more. It's a little bit greedy because we have some. We have separable. We can do first order linear. And today we're going to come up with a third one. And it involves something called an exact ODE. And ODE is shorthand for ordinary differential equation. And so what is that? Well, it's a very particular thing that happens. So suppose that we have a differential equation written in the following way. So there's some function. So here when you say m of xy, it's some function of x and y dx plus some other function dy equals 0 with the following situation going on. And this is what makes it exact. So it's not exact if it's in this form. There's this condition here. And now we have to talk about the symbols. All right. So the symbol here, this symbol, stands for partial derivative. And the idea says, oh, I have something which depends on multiple inputs. So you'll notice that m depends on multiple things. It depends on x and on y. So here it says we're taking a partial derivative. So we're taking a derivative of part of it. Which part? Well, of y. So we're taking the derivative of this m with respect to y. Now, when I'm taking the derivative of m with respect to y, how do I think of x? As a constant. That's the key idea. And that's going to be something, this derivative of m with respect to y. And now we say, well, hey, compare that to the derivative of n with respect to x. And that's going to be something. And when we take the derivative of n with respect to x, how do we think of y? As a constant. Yeah. And we compare these two. And if these two are the same, then it's exact. All right, so that's what an exact ordinary differential equation is. Now, why do we care? Well, it turns out that there's this really cool fact. And it says, all right, when is a differential equation exact? And it's a very strong statement because it says if and only if. So in other words, we know exactly when we have something that's exact. And the answer is that there is some implicit relationship f of xy equals a constant, where when we take the derivative of this function f with respect to x, out comes n. And when we take the derivative with respect to y of this function f, out comes n. And so we say, aha, great. So, well, we need to understand a couple of things. And so let's start with a few key words here. Implicit. So we've probably encountered that before. What does it mean when we say something is implicit? Yes?
It's implied, like it takes a moment to get there, but it exists.
Okay, so there's something that exists, but okay, there's an implied relationship. That's not a bad way to think about it. Probably, I'll start by saying there's this notion of like, well, let's talk about explicit. You know, we can say, well, what's implicit? It's something that's not explicit. You're like, well, what's explicit? Well, something that's not implicit, right? And then, okay, no, that's not going to work. Okay, so when we talk about explicit, what we really say is, look, these are relationships where we can solve for a variable. So that says something like y equals stuff with x. That's a nice explicit statement. You give me x, I throw it into my machine, out comes y. Or I could have x equals stuff with y. That's okay too in certain settings. It says, look, there's this clear relationship. You give me x or you give me y, I can get the other variable. That's when we have things which are explicit. So what's implicit? Well, when we can't do that. And at least not in those terms. So you might have something like y squared x plus e to the y plus cosine 2x equals 7. Here, there's no way to get y by itself using standard tools. And there's no way to get x by itself using standard tools. And the reason I say that is I say, well, look, there's a y here and a y there. Whatever I do to get the y out of the e to the y will throw that y squared inside of a log. Or, if I try to get that y out, well, then this is trapped. They're separated. There's no standard tools that help us write it. Nevertheless, it doesn't say that x and y are completely independent of each other. What it is that there's some relationship. We just cannot explicitly write what it is using standard tools. So there is some function y which depends on x, but we don't know what that function is in an explicit way. So that's what we mean when we talk about implicit, is when we just get some sort of expression. And we can't necessarily solve for one of the variables. Sometimes we can, but usually we can't. So that's what an implicit relationship is. So it's just stuff that involves x and y equals either a constant or more stuff involving x and y. All right. Now, let's also understand why this is so good in terms of our goal here. Our goal is to solve a differential equation. So, suppose we start with our function f of xy equal a constant. Well, what we have is that we have this relationship. And so there's an implicit relationship. In other words, y depends on x. We just don't know how. But because we have this relationship, we know that there's something going on. So I can think of there being a variable tree. In other words, how do things depend on each other? And I can say, well, look, the function depends on two inputs, x and y depends on this input called x. Now, if you've taken calculus or if you've taken multivariable calculus, we've gone through this before, and if you haven't, that's okay. You don't need to understand too much here. We'll get to the punchline, which is how do you actually solve this in just a few moments. But now what I'm going to do is I'm going to say, let's take the derivative of both sides. And I'm going to take the derivative of both sides, when I say of both sides, of this equation, f of xy equals c. Take the derivative of both sides with respect to x. Now there's two sides, so we'll split the work. I'll do one side if you do the other. I'll even let you pick. Which side do you want to take the derivative of? Okay, so people seem to want to take the derivative of the right-hand side. So we're taking the derivative with respect to x. What do you get? Yeah, you get 0. It's a constant. Okay, so we have made progress. So taking derivative with respect to x, we have the right-hand side is 0. All right. Now, the left-hand side, that's my job. And to do that, I say, well, look, I have this function f, and I say, well, how does x influence the function? And I can actually see it because I understand how the variables relate. And I can see that there's two effects that go on. So one way that x influences the function is directly. And so that's all right. We say, okay, that would be partial f partial x. But it also does it indirectly, because the function is influenced by y, and of course x is influenced by y. Sorry, y is influenced by x. So I have to take into account this other avenue here. Now this other avenue, I say, well, how does the function change with y? And how does y change with x? And I put those together. Now, for those of you who are very nitpicky, you might say, Steve, why do you use the partial symbol there, and right next door you use the d symbol? Do you know the answer to that? It's not a typo, it's actually deliberate. Sorry, what?
The one on the right is not
Yeah, okay, so someone said the one on the right is not a partial. That's the right idea. Because notice, what is f? F depends on two inputs, x and y. And here, what is y? Well, y depends on one input, x. So we use the partial symbol when there's multiple inputs, the d symbol when there's only one. Now, those are the two effects. To get the total effect is to add. All right. So, what's the punchline? The punchline says, hey, this left-hand side is actually the derivative with respect to x of f of xy. And we know that the easiest thing to integrate is a derivative. And so what's really going on here is when we have something that's an exact, this side here is coming from a derivative. In particular, this m of xy, this is partial f partial x. And right next to it, this n of xy, this is our partial f partial y. So when we're exact, it's coming from a derivative. And so we can integrate. So that's why we have a chance. A chance. All right. So that's the background. How do we actually do it? All right. So I can tell you a very slow process that carefully builds up and gets the answer. Or I can say in practice, this is what you do. Do you have a preference? You want to see the slow way? Or do you just want to say, look, here's the way, it's quick, it's easy, and you just bang it out in 30 seconds. I don't care which way you want to do it.
Let's build it up.
Build it up, wow. The other class was practical. They said, just show us how to solve it. We don't need to go slow. It doesn't go any slow. It doesn't make it any faster. Okay, so here's how we do it. So let's suppose we know it's exact. Can we know it's exact? Yeah, there's a test. This essentially right here is your test for exactness. So I can know if something is exact by just checking these partial derivatives to see if they line up. And by the way, we should actually say, why does it make sense that if we are exact, those partial derivatives agree? Let's think about what's going on here. So where does m come from? Well, I took a derivative with respect to x. And now I'm saying take a derivative with respect to y. So I took one derivative with respect to x, and then I took a derivative with respect to y. And that's the result that's here, this m derivative with respect to y. Where did n come from? Take the derivative with respect to y, and then take the derivative of that with respect to x. And notice it's still two derivatives, one with respect to y, one with respect to x. So it says either, look, if you take the derivative first with x and then y, or then y, then x, you should be the same. That's what the check is. Just saying, hey, these derivatives should match up. Okay, so here's sort of the way you can do it slowly. We say, look, I know partial f partial x is equal to m. How would we get f? We'd integrate, right? Because this is a derivative. And one of our mantras is it's easy to integrate a derivative. What should we integrate with respect to? X. Okay, so now we integrate with respect to x. And if we do that, what will we get on the left-hand side? We'll get f. Because we took a derivative and then we integrated. All right, so we're back to f. All right, that'll be the integral of this m dx. What am I missing? Plus c. So, is this correct? And why not? Okay, so someone said, you got to account for the y terms. So it is not correct. Now, you might say, well, wait, hold on. Why would it possibly not be correct? Well, because we integrate with respect to x. So when I talk about a constant here, I'm talking about constants as far as x is concerned in the process. So when I'm integrating with respect to x, how do we think of the y? We think of them as constants. So this is a constant function of y. So now the problem says, well, how do you find that? Well, good question. What can we do? Have we used everything yet? No, we haven't used something, right? We haven't used this information. So from here, what we can do is we take the derivative with respect to y, and we set that equal to n. All right, so you integrate with respect to x, you got an expression, take the derivative of that with respect to y, set that equal to n. And when you clean it up, you'll get c prime of y equals just stuff with y. That's what you'll end up with. And now, what do you do? Well, you can integrate, and you can find c of y. And here it'll just be a function of a single variable, so we just say integrate. We don't even have to say integrate with respect to y. And once you find c of y, lo and behold, you found f, and you're done. Okay, so that's how you can do it. So, in one way. Let's talk about another way you can do it, by example. Any questions before we leave here? We've said a lot. I don't want you to feel too overwhelmed here. It's much easier than our discussion makes it seem. Are you ready? All right. We're ready. Okay. So, we're going to solve. So we have 2xy squared plus 3x squared dx plus 2x squared y plus 4y cubed dy equals 0. We want to solve. In other words, we want to find a relationship here. Now, what can we do? Well, first off, we might ask ourselves the question, is this exact? And we can actually answer that. Okay, so let's quickly answer it. We look at what's attached to the dx. We'll think of that as one function m. And what's attached to the dy, we'll think of that as the other function n. And now, what's the test? Yeah, we compare partial derivatives. So it might be helpful to remember what these are supposed to be. If it's exact, what's attached to the dx says, oh, that came from the derivative with respect to x. What's attached to the dy is, oh, that came from the derivative with respect to y. When we're checking for exactness, we say, okay, sort of do the opposite. So if here this came from the derivative with respect to x, we can say what happened to the derivative with respect to y. So partial and partial y, what happens? Well, what's the derivative of 2xy squared when we take the derivative with respect to y? 4xy. What happens to, okay, and the derivative of 3x squared when we take the derivative with respect to y? 0. Why 0? Because it's a constant. Okay. And then we say, well, let's look at partial and partial x. All right, what's the derivative of 2x squared y with respect to x? 4xy, that's good. Derivative of 4y cubed with respect to x? 0. So these partial derivatives match, which means, is it exact? And the answer is yes. We can definitely say it's exact. All right. So now we know that we're going to succeed modulo our ability to integrate. Okay, so I know I outlined a procedure, but I just want to show you in practice a way that's a little bit faster, and I'll explain the ideas. I say, look, we know we have our partial f partial x. That's 2xy squared plus 3x squared, and our partial f partial y. That's 2x squared y plus 4y cubed. And now, what we do is we're going to integrate both of them. So here, I'm going to integrate with respect to x. So integrate partial f partial x with respect to x. That'll give me my function. What happens when I integrate on this side? What do I get? So integrating 2xy squared plus 3x squared dx. What's the integral turn out to be? X squared y squared plus x cubed plus c of y. And now I'm integrate this other part. Integrate partial f partial y dy. Well, that's going to be f. Okay, that's the integral 2x squared y plus 4y cubed dy. What's the integral of 2x squared y with respect to y? X squared y squared. Integral of 4y cubed with respect to y. Y to the fourth. And then some function. I'll move our way up through the alphabet because it's not the same function, so I'll use d. Some function which depends on x. And now what you do is you just do a comparisons and say, okay, so how do I find f? The key is you say anything that just only has x has to be included. All right? Is there anything with only an x? X cubes. So you have to have only x. Those always have to be included. Plus, now you do the same thing with y. Is there anything with only y? Y to the fourth. And that has to be included. And then, one more thing is you have to say, okay, the other thing is you have to check both x and y. And now, this is our time to check. What we need is we're not going to include them both. So we don't need x squared y squared and another x squared y squared. So it doesn't become 2x squared y squared. But they have to match. If they don't match, it's not exact. So do they match? Yeah. And so we include it. And now, that's our function. Are we done? What are we missing? Well, our solution, yeah, plus some constant. And so in general, we're going to have that our solution will look like that. Now, you might notice a couple things. Let's point them out. The function that only depends on x is actually being part of that d of x. So that d of x includes that x cubed. By the same token, that y to the fourth is also inside of that c of y. And that's why we integrate both pieces, so we can pick up that missing part. We can see what's going on.
So you're not saying that d of x is 3 cubed. You're just saying that 3 cubed is part of d of x.
I am saying that d of x is x cubed plus a constant. Yeah. And that's what it'll turn out to be. And c of y is the y to the fourth plus a constant. Yeah, that's the process. Now, by the way, I'll answer your question in just a second. Do you actually have to check if it's exact? And the answer is no, you don't. You can just run the process, and if you get to a point where these don't match, then the answer is it wasn't exact to begin with. And so there's sort of a built-in exact check. Yes, you had a question.
So it equals a constant e?
Yeah, because what we're after is when we talk about solving an exact ODE, if I'm just after the function f, I'd add a constant. But when we talk about a solution, we really say, look, we want a function equal to a constant. So that's why. It just matters where you want the constant on the left or you want the constant on the right. So we're following the convention that we put the constant over on the right. Yeah, so in case you're wondering what would have happened because the other class, unless they fix the notes in the last few days, is going to find out that, whoops, they're going to start with something which is not exact. So you can imagine that we had something that looked like this. And so if you just skip the checking, if you run the partial derivatives, they won't match. But what will happen is you'll get to a certain point, and when we integrate it here, you get x squared y squared plus x cubed plus some function of y. And then here you'd get 2x squared y squared plus y to the fourth plus some function of x. And when the parts that involve both x and y, when those don't line up, it means you didn't have anything exact and you just stop the process and just write not exact. So if you feel very confident that it's an exact and you just want to rush in and start doing integration, yeah, you don't have to do the check at the beginning. Yes?
You get that your answer is not exact. Do you have to solve the problem a different way?
You have to look for other approaches. Now, you might ask the question, well, do we have to do some sort of manipulation and say, oh, maybe if we multiply everything by x, it becomes exact? And the answer is no, just abandon all hope. Well, maybe not abandon all hope, but say, well, maybe it was really a linear first order in disguise or something else. But yeah, if it's not exact, it just means that this approach won't work, and you just stop. Other questions? Okay, well, another example then. We should do another one. All right, arctangent, cool. We'll get to integrate something with arctangent in it. All right, so solve x plus arctangent of y plus x plus y over 1 plus y squared, y prime equals 0. Now, you might say, we can't even start this one. It's not the right form, Steve. Okay, all right, hold on. You don't like it now because there's not that dy dx, but how do we think of our y prime? Yeah, we think of this dy over dx. And what we do is we say, well, look, let's just imagine we split it. So this really is x plus arctangent of y dx plus this other stuff, x plus y, 1 plus y squared dy equals 0. So that's, we can go from something with y prime into this sort of differential notation. And we have our hints here, right? The dx part says, look, this part right here should be the result when we take the derivative of the function we want, which I don't know if I said it explicitly. We sometimes call this function f a conservative function. This is a convention you might hear in physics or multivariable calculus. So the part that's in front of the dx, that's the derivative with respect to x. The part that's in front of the dy, that's the derivative with respect to y. All right, so we're just going to go on faith that this is exact, and we'll check. There's a built-in check at a certain stage. And now we say, let's just go for it. Let's do our integrations. So, f. We're going to integrate the derivative with respect to x dx, because it should be easy to integrate a derivative. All right, so we're going to integrate x plus arctangent of y. Oh, this is going to be good. Integration arctangent. Woohoo! Nice. Okay, integral of x. 1/2 x squared. Integral of arctangent y is? Yeah, arctangent y times x. Because keep track. We're integrating with respect to a particular variable. So we treat arctangent of y like a constant, because arctangent depends on y, and y is treated like a number. Like if you integrate 4, you say, oh, 4x. Well, it's just a very fancy-looking 4 right now. All right. So all right, that says x arctangent of y. All right. Now, the other piece. Partial f, partial y, dy. Well, let's break that up. So x over 1 plus y squared and y over 1 plus y squared. And we're going to integrate that dy. How about this first piece? the integral of x over 1 plus y squared, integrate that with respect to y. What do we get? Yeah, x is a constant, and then 1 over 1 plus y squared will be arctangent. And we kind of should expect it. Why should we kind of expect something that looks like x arctangent y? That's in the other one. And anytime you have variables mixing, they have to show up in both. That or what you have is not exact. Now, the fact that when the variables mix, they agree, that means it's exact, at least so far. But it looks like nothing is going to change our faith in that. How do you integrate this part? Y over 1 plus y squared. Okay. Substitution. What do we substitute? Okay. U is 1 plus y squared. What would du become? 2y dy. Well, okay, so let's make a 2 there. Am I allowed to do that? Well, I am if I fix it, right? How do I fix it? Multiply by half. So then you have 2y dy, that part will become our du, and then this 1 plus y squared is our u. So we get the integral 1/2, 1 over u du. What does that become? Oh, whoops, we didn't finish that integral. Oh, we got sidetracked. What did we miss? Yeah, some function that just depends on y. Sorry about that. I was just so excited about the arctangent, just got my blood pumping. It happens to all the best of us. Okay, back to this integral. What do you have? 1/2 log u, which is 1/2 log of y squared plus 1. Okay, so updating, we'll have 1/2 log 1 plus y squared. Anything else? Yeah, something that depends just on x. And now we just do our quick check. As we said, we've already ran our check, which is to compare the things that involve both x and y. They match. So that makes us happy. So we can smile. So that means it's exact. And we can write down what our function is. So our function, well, what will it contain? Okay, 1/2 x squared. Okay, and I should say there's nothing special about the order. Just make sure you grab what you want. So yeah, we can do the y part next. So 1/2 log 1 plus y squared. All right, x arctangent y. And then there'd be a constant. So this is our function, that's our potential function. And so the solution to the differential equation, what would we do with this? Yeah, we set this whole thing equal to e. And that says that the solution to this differential equation is this expression. Now you might look at this and say, we'd never be able to solve for y. You are correct. Could we solve for x? Yes, we can. How? Rhymes with schmodratic formula. Yeah, that's a terrible rhyme. It's a quadratic in x. Something x squared, something x constant with respect to x. So yeah, you could. You would never do it. Only if you were like really mean to someone would you solve for x. But yeah, you could. So, all right. And that's kind of the flavor. It's actually not a bad process once you get the hang of it. You say, okay, in essence, I have this function f I have to reconstruct. And I have the derivatives. One derivative with respect to x, one derivative with respect to y. So we say, okay, take the respective integrals, just compare, and grab what you need, and put it all back together. And there you go. That's the idea. That's the idea. All right, so this is the last part of the exact. Any questions before we move forward? Yes?
Yeah. How do you choose what is n, what is n? Is it by order?
Well, you look at the dx piece and the dy piece. And so don't worry so much about m and n as just saying what's in front of the dx piece should be the derivative with respect to x. what's in front of the dy piece should be the derivative with respect to y. And if you can remember that, that helps you understand how the process flows.
From the equation itself.
Well, because when you ask about which part is m and which part is n, the m part back here is what's in front of the dx, and the n part is what's in front of the dy. But for me, I don't want to say m and n, because those are just symbols. I like to say, well, what do they represent? And that helps me. I think there was a question somewhere else. Sure.
Is it possible if there was like two different x's in both equations, single x variables, what would you do then? So like in both of the f's, there was like 1/2 x squared and like 1/3 x cubed. Do you include both in the final equation?
Well, if you had a 1/2 x squared and a 1/3 x cubed here, then...
And on the second one as well.
Well, you wouldn't. And here's why you wouldn't. Is because what happens is, where could you get a 3rd y cubed? Well, the only way you can get a 3rd y... Oh, wait, hold on. Sorry. A 3rd x cubed down here in this equation, it would only be part of the d of x. Because we're integrating with respect to y, so everything here has to have at least something with y in it. You can't have only x pieces showing up here. So everything that's only x will only show up in this first integral when we integrate with respect to x. And things which are only y can only show up in this second integral. So you'll never have that crossover happening. Are we good? Okay. All right. Great. Well, let's do a quick summary of where we're at. So we've talked a lot about first order differential equations. And we have more or less sort of 3 things that we actually can handle. So this is more, you think about this, the first part of the course, this is what we've done. We say, okay, suppose we see a first order differential equation. We look at it and say, can it be separated? Is it separable? If it is, well, then we run the process. It says separate it, integrate it, uncomplicate, and we solved it. Well, maybe it's a linear first order differential equation. And if it is, then okay, find the integrating factor, and that helps us to integrate. So we multiply both sides by the integrating factor, we integrate, and we're ready to go. The third thing we say, well, is it exact? If it is, we talk about what we just did, and we say, okay, we find that function, that function capital F, that potential function. And then life is good. And the other thing that we've talked about is not really necessarily a method, but it says, well, what else can you do? Because you might not be any of these. And so the other thing we talked about is say, hey, perhaps there's some way we can do a substitution or some sort of algebraic manipulation to take our differential equation and transform it. So it does fall into one of these categories. By the way, I'll say it again. Don't worry about trying to make something exact. If it's not exact to begin with, then just forget it. Don't even try to make it exact. But maybe there's some kind of substitution that transforms something from being not separable to separable, or taking something that's not linear to linear. And that's what we talked about with substitution. And there's a warning at the bottom. And you might think, wow, so far we've had like 100% success rate in solving these differential equations. So it must be the case that we can always solve. No. If a person walking down the street just randomly hands you a differential equation, forget it. Hopeless. Hopeless. Especially if they're mean. But even if they're nice, it's still pretty hopeless. Because it's so easy to have things be very, very hard to integrate. And at the end of the process, all of these techniques we've talked about involve doing some integration. And if it's one thing we learned from our Calculus 2 course, integration is hard. It's easy to get stuck. So that's what we've learned in the first part of the course. All right. So, in the remaining 5 minutes, what we're supposed to talk about today, which is population models. And it'll take about maybe 10, 15 minutes to do the whole thing. So we'll just do the first 5 minutes, and then next time we'll do the remaining 10. So differential equations are very useful when we talk about modeling population, because oftentimes when we think about populations, we think of them as how do they change. And once you start saying, well, I'm interested in how things change, what you really have is saying, hey, I'm interested in the differential equation, because differential equations are about change. And so we say, well, how can populations change? And we'll group them into sort of two categories. Things that can increase the population we'll call births. Things that decrease we can call deaths. And so we have this birth rate. And the birth rate may be a function of t. So it might change as time changes. And the death rate, which again is a function of t. You notice that the book uses beta and delta, because, beta, birth, have the B's going on. Delta, death, have your D's going on. So we say, okay, the change in population, well, you take the birth rate times the amount of population, because we're thinking of that as a rate. So the birth rate isn't how many people are being born, it's the rate at which people are being born. So when you multiply that by p, okay, that's the total number of people born. And then the death rate, similarly, multiplied by p, that's the total number of people who pass away and die. And so what we get is this beta minus delta times p. So the first case, which is very simple, says, well, suppose that these are just fixed numbers. So then, say, great. If these are fixed numbers, that means they don't change. What we really have is that the change in population is somehow proportional to p. And this is one of the first kinds of separable differential equations we learned. Very straightforward to solve. And so we have a nice general solution. It says our population behaves like some initial population, e to the kt. Now, let's just point out a few things that could happen. What would happen if beta were less than delta? Let's just think about our intuition. So here's our initial population. Births are smaller than deaths. What should be true? If births are smaller than deaths, wait, what is it? Our population should shrink. Because we're losing people. We're losing them faster than we can replace them. Now, that would be what? Well, that says really, hey, k is negative. What does that happen? Well, that says you have an exponential function with a negative exponent. So we have exponential decay. And that's what the model says. That's good. All right, well, what would happen if, say, beta is greater than delta? It should increase, right? Yeah, because we have that k should be positive. And then we have exponential growth. Now there's one more case. What if beta equals delta? What happens then? Yeah. And you can even see it in the differential equation. You have 0 times p, which means that your p prime, your change is 0. Well, if your change is 0, it's always the same. All right. So that's a really simple case. Then we spice it up a little bit. Well, maybe things aren't always constant. What could happen? Well, it might be the case that the birth rate starts going down as population grows. People aren't encouraged to have kids. They're expensive. Or something else is going on. Who knows? You could have, in a similar way, this, well, maybe the death rate goes up as your population grows. Because why? Well, more people, more competition for resources. And so there might not be as many resources to spread around, which causes death rate to go up. Either way, we have something going on. So we can say, well, suppose the birth rate looks like a constant minus a constant times the population. So that just says population goes up, birth rate goes down. Well, you feed it in and say the change in the population looks something, you have your births minus your deaths. And you move it around, you get a constant times population times another constant minus the population. Now, we've seen this before. Do you remember it? Well, Newton's law of cooling would be if we didn't have that P. Anyone remember the name? Yeah, it's logistic. And we actually solved it. Now, I was gone for this class. I don't know if you did it in class. But if you missed it, there's a recording. And that's what it becomes. Why? Well, this is separable. And then we get to do fun stuff like partial fractions. And there we go. Now, in the last -1 minute, let me just point out some things. When does p prime equal 0? For what values of p does p prime equal 0? 0 and m. All right, if I have p equals m, and this m is sometimes called the carrying capacity. And now what happens is if k is positive, you're going to go up. And so if you're below your carrying capacity, you move up. If you're above your carrying capacity, you move down. And so that's what happens here. That's the reflection of the equation. I will say if k is negative, you get something really weird going on. But, you know, why should we let k be negative? Just because it's weird, stop us. So namely, if k is negative, it will go away or it'll blow up. And we'll talk more about what happens in these situations next time. That's it for today.